The objective of this video is to introduce permanent magnets and develop their magnetic equivalent circuit model. Up until now, we've been developing magnetic equivalent circuits using Ampere's law and considering the magnetomotive force as being produced by current linkage. That is, we evaluate the integral of h.dl along an enclosed path, and we set it equal to the integral of the current density within the surface of that path. And it turns out that there are two sources of magnetomotive forces. The first source is this enclosed current, this physical current that we've been talking about. And the second source is permanent magnets. And permanent magnets, as we'll show in this video, can be modeled as an equivalent current linkage. The point of this video is first to introduce what a permanent magnet is and how we think about it in terms of a magnetic material. And then second, to develop a magnetic equivalent circuit representation of a permanent magnet so that we can use it to design the permanent magnet to give us a desired flux or a desired flux density. Let's start by considering permanent magnets as a magnetic material. And the ultimate simplistic description of a permanent magnet is that a permanent magnet is simply a magnetic material with a very large hysteresis loop. So let's unpack this a bit. What do we mean by saying a material with a large hysteresis loop? We'll start by drawing the BH curve for iron, for steel that we use in the motor laminations. And we've talked about this a bit before, how we can graph the magnetic flux density within our core as a function of the H field that we apply. And in the past, when we've drawn this graph, we've sketched it to look something like this. And we've noted that we have a linear region over here, and then we have a saturation region at each extent. However, that isn't the whole truth. In actuality, when we push our material to saturation, and then we come back down from saturation, we experience hysteresis. So that means that if we start off magnetizing our steel like this, and then we get way out here, and now we decide that we're going to back our steel down. We're going to apply H in the negative direction. We end up actually observing a behavior like this. That is, we have hysteresis. We don't trace back our original path exactly. If we then start to apply H in the other direction, we get a characteristic like this. And this is a bit of an exaggerated curve, but this is to demonstrate the point here. And so we've approximated it in our models in our FEA tool as being this blue line, but in actuality it takes this green path. And where you are in that curve depends on the history, on where you have been. And we can exploit this property, this dependence of our magnetization state on our history, to create a permanent magnet, to create something that is always magnetized. And the basic idea of a permanent magnet is that we always stay within this region up here, so that when we're applying no H field, we have some magnetic state. And so basically a permanent magnet is a material that has been optimized or improved to stretch out this region. And let's now sketch the BH curve for what a permanent magnet looks like. And we're going to do this with one modification. Instead of having our x-axis be H, we're going to have it be mu naught times H. And the reason that we do this is because magnets typically have a relative permeability of approximately 1. And so if we normalize this by mu naught, we can see the characteristics of the curve a bit better. And so what we have for a permanent magnet is a curve that resembles this. Where we can relate this back to our original iron diagram by noting that this point right here, where we sit kind of on a knee, corresponds to this point over here. We again have a knee. And way out here, deep in saturation, corresponds to something out here. So you can see that the magnetic BH curve looks different. It exaggerates that region. And the slope of this line is mu r. The reason it's mu r is because we're graphing B versus mu naught times h. So the slope of this line right here is mu, because in this case we have no mu naught in front of h. Okay, when we operate a magnet in a magnetic circuit, our operation range is in the second quadrant of the BH curve, and so we'll now zoom in and sketch that down below. And so if you pull up the BH curve for a magnet from the magnet manufacturer, you're going to see a curve that looks like what I've just drawn. You're going to see something that looks like this. They're not going to bother showing you this entire BH curve because you're only interested in this region right here. We call the y-intercept here, when mu naught h is 0, we call the value of b at this point br, which stands for remnants, or residual flux density. And that is the magnetization of the magnet. That is how you know it has been magnetized. We can write the expression for the magnetic field within our magnet as being B is equal to the remnants plus mu naught times h. So mu naught times h is what we normally see for any magnetic structure. And our remnants is the bonus that we get for this being a permanent magnet, for having energized it out to the point of saving a magnetization state. And so the way that you get this is that the way that you get this characteristic is that you've got a material that exhibits this BH curve that we've shown up above here. And when you initially get your material, you're going to sit at this point right here. And so what you do is you put this thing in a very large magnetic field that pushes your magnetization state way the heck out here. And then when you turn off that magnetic field, the magnetization state falls along this line here, the top purple line. And so that's called a magnetizing fixture. It's part of the manufacturing process for permanent magnet motors, is that you first make your magnets and then you put them in the magnetizer and you blast them with this immensely strong field. And then as long as you stay above this point, so as long as you operate your magnet in this region here, you do not alter your magnetization state. That is, BR remains the same. And this point that I've identified here, this is called the knee of your BH curve. And if you push your magnetic field below that knee, if you somehow end up down here, or down here, or down here, when you remove your H field, you're going to, it's called recoil. Your BH curve will take a new trajectory back up here, and you can see that now you have a new y-intercept, and that means that your magnetization state has changed. You've actually altered BR at that point. If you go far enough down this line, you will actually recoil to zero magnetization. The value of H that causes your magnet to become completely demagnetized, the value of H that leads to BR equals 0, is called your intrinsic coercivity. and this is usually represented as HCI. The value of H that causes your magnetic field to cross the 0 Tesla line is referred to as your magnetic coercivity, and that's usually labeled as HC. So let's add these definitions below. And the coercivity is solved from, we can calculate that from our equation up here by saying 0 is equal to BR plus mu times H when H is equal to HC. And if we solve this, we get HC is equal to a negative BR by mu. And our intrinsic coercivity, we said, is the H field that is needed to make our remnants equal to 0. It's the H field that when we push it down to this purple point, we end up, when we recoil along our trajectory, we end up with no remnants. We see that we cross when H is equal to 0, and all of a sudden B is equal to 0 as well. And these are properties that you will need to know the name of and be aware of when you look up materials on a manufacturer's website, as well as when you enter material properties into your FEA tool and try to set up a simulation that has permanent magnets. And then also, relevant to this lecture, when you need to know these properties in order to determine the magnetic equivalent circuit of your permanent magnet. We commented that pushing below the knee partially demagnetizes the magnet. And when we're saying pushing below the knee, we mean that we're pushing our magnetic field below that point. So we're somewhere down in this region. And therefore, when we design our motor, we will always want to operate the motor above the knee. Or we risk demagnetizing our motor, and then we no longer have a machine capable of producing torque. And the important thing to watch out for on this is that this BH curve characteristic changes with temperature. So this was our BH curve for one temperature. Maybe it's room temperature, maybe it's 100 degrees C. But if you look at it for a different temperature, the curve pulls in, and so it would look something like so. As we increase our magnet temperature, you see that the whole curve pulls in, so we effectively have a lower remanence. But more concerning, our knee now is occurring in the second quadrant. And so if we design our machine so that we always stay above the knee, we always stay in this region up here, even at elevated temperatures, we're always above the knee, then when our magnet cools back down, we will go back to the original BH curve. Our original remnants will come back. But if, when our magnet is elevated, if we end up operating somewhere down here below the knee at the elevated temperature, then we demagnetize the magnet permanently, and we will no longer recover our original curve. So when you design your motor, you have to be very careful that you design it so that at the maximum expected temperature, you are still above the knee on your BH curve. Okay, so these are some of the salient properties of permanent magnets. Let's now briefly talk about the three most common types of magnets. So by far the most popular type of magnet are ferrite magnets. And that's because these are the most inexpensive magnets, which makes them popular. However, they're also the weakest and the lowest performance magnet. So by weakest, I mean that they have a low BR, and their knee occurs further to the right. So this pink line that I drew for the increased temperature is what you typically see for a ferrite magnet compared to one of the more expensive magnets where your knee occurs further to the left and your remnant field is higher. For high performance machines, you're talking about either neodymium iron boron magnets or samarium cobalt. And neodymium iron boron magnets are expensive and they're made of rare earth materials. There's a whole host of challenges with this. Rare earth materials are difficult to mine, difficult to process. They have environmentally hazardous impacts if not done properly. But the payoff for electric machines is that these magnets are the strongest. They offer you the highest BR, and their knee is further to the left. And all this translates to a higher performing motor. That means more efficiency, that means more compact, and less usage of other materials. The second rare earth magnet type is samarium cobalt. And we can also say that these are expensive and they're rare earth. And so while we said neodymium was the strongest, we should qualify that. Neodymium is the strongest at low temperatures. Samarium cobalt is the strongest at high temperatures. So in 99% of the motor designs that you'll ever be exposed to that use permanent magnets, you'll use one of these three types of magnets. Let's now develop the magnetic equivalent circuit for a magnet. Suppose that we have a cubical magnet, and this magnet is oriented so that it has a field that is coming up axially and entering in the bottom. And this is going to be a flux tube. So this here is going to be surface 2, here's our surface 1, and so we have a node on each of these surfaces. And this flux tube has a constant cross-sectional area A and a length of L. And so we can write that our total flux to the flux tube is equal to B dot ds, which is just equal to our magnetic field times our cross-sectional area. And if we plug in our magnetic field equation, if we plug in this equation here, we get the following expression. And if we work on this a little bit, we can notice that this first term here is our remnant flux density times our cross-sectional area, and that looks like a flux. We'll call that flux R, so our remnant flux. In the second term, we can parse this out in two ways. The first part of the second term looks like a length divided by the reluctance of this flux tube. And the last part, the H field, we can consider this as the magnetic voltage across our flux tube divided by the length of our flux tube. So if you go back to our previous video introducing magnetic equivalent circuit elements, you can parse out how we are identifying these expressions. And so we can say then that our flux is going to be equal to a remnant flux plus our magnetic voltage divided by the reluctance. And this looks like a circuit element that we can draw. So if we start to draw this, we can say that we've got a current source, which is phi r. So we're again looking for an expression of our total flux. It's going to be that current source, plus it's going to be the voltage that appears across the reluctance of our flux tube. So this would be node 1 down here, and we've got node 2 up here. That means here's our reluctance, and we've got a voltage, a magnetic voltage here. And long story short, this is the magnetic equivalent circuit model of our permanent magnet. But let's tidy some things up. So the reluctance of our magnet was equal to the length of our magnet divided by mu times our cross-sectional area. And the voltage across our magnet is just equal to H times L. And these are from the definitions of these elements, of these quantities calculated for this flux tube. So So that's nice, but in this class, a lot of the time, we'll be actually talking about magnets that are on a shaft. So they're actually going to be arcs. And it'll be a geometry that looks something like this. And so in this case, we're assuming that our magnet goes into the page a depth of L, capital L, and that it has a thickness or height of lowercase l, so corresponding to this, and it has an inner radius of Ri. So in this case, our magnet does not have a constant cross-sectional area. In our previous example, we said that our magnet had this constant cross-sectional area of A, but now we have a different cross-sectional area at each radius within our magnet. And so what we do is that we can calculate our reluctance using an integral. A differential, each layer going radially outwards, we have a series of differential reluctances that have a thickness of dr and a cross-sectional area of r times alpha m times our length into the page. And so to evaluate this integral, we're going from an inner radius of Ri to an outer radius of Ri plus L. That is, we're integrating from this point right here out up to this point. And so if we evaluate this integral, we get the following expression, which has a natural logarithm in it because we've got r in the denominator. And we can simplify this expression to give us the following expression. So you can see that we can do things like this. We can use calculus to determine the reluctance for custom-shaped objects. And in this case, we worked this out in this video with you because it's going to come up time and again. We're dealing with motors, so we're dealing with magnets on shafts or magnets on laminated steel. The final thing that I want to talk about is the Norton equivalent and the Thevenin equivalent circuits. So as we've currently sketched this magnetic equivalent circuit is in the Norton canonical form. That is a Norton equivalent circuit. And so what we're going to do is we're going to put this into the Thevenin equivalent circuit format, because oftentimes the Thevenin form is more useful for design purposes. So the Norton form consists of a current source in parallel with a resistance. The Thevenin equivalent circuit, or the Thevenin canonical form, consists of a voltage source in series with a resistance. So in our case, it's a current linkage in series with a reluctance. And if you'll recall, you can convert between these two forms by simply multiplying your resistance by your current source to determine the voltage source. And we're going to denote this as a current linkage. This is going to be the equivalent current linkage of a magnet. And if we assume that we've got the simple geometry that we had up here, we can plug these expressions in and simplify our current linkage form. So this means that the equivalent current linkage of a permanent magnet is the remnant flux density times the length of the magnet divided by the magnet permeability. And this gives you a lot of design insight. So if you've got a magnet that you're using to magnetize your circuit, and you want to increase your field in your magnetic circuit, this shows that you have a few options. You can pick a magnet with a larger remnant flux density, but if that's not an option, you can increase the length of the magnet, you can increase the height of the magnet. And that makes more sense. You've added more magnetic material that is now able to push flux along this path. So when you're analyzing a magnetic structure and you've got a permanent magnet and you want to sketch the magnetic equivalent circuit, you're going to plug in one of the following equivalent circuits into your magnetic equivalent circuit to model the permanent magnet. So you've got a series of reluctances, a series of flux tubes, a network of flux tubes, and you've got a magnet in this network. You model the magnet within your network of flux tubes by one of these equivalent circuits. They're both equivalent, so the circuit that you choose should be the one that's most advantageous for solving your broader network of reluctances. Let's summarize now. In this video, we've introduced permanent magnets, and we've talked about what their BH curves look like and defined the salient features of permanent magnets. And those salient features were the remnants, or the residual flux density, their coercivity, their intrinsic coercivity, and their knee, and finally the governing equation for the field within the magnet. We define the most common magnet types as being ferrite, neodymium iron boron, and samarium cobalt. And we've introduced a magnetic equivalent circuit model for a permanent magnet. This magnetic equivalent circuit model is something that we'll be using to study the magnetic fields in our machine cross-sections